All right. Well, I guess we have to redo the hello hackers. Hello hackers. All right. And what's going on with Twitch? It's like it's like magic. All right. Hope everybody is excited for Baby Mem. I'm excited for Baby Mem. This really gets us into into something approaching real hacking, right? Reverse engineering is really good, super fun, of course, but it's kind of a program understanding. You can imagine a reverse engineer, doing reverse engineering for making cracks for games, etc., etc. It doesn't quite get you into the controlling software with your mind aspect. And that's where we're going now, which is going to be super fun. And especially where we'll solidify for next week with Toddler 1. It's going to be great. You are all going to love Toddler 1. This year we have a nicer, kinder, gentler, but also more intense Toddler 1. It's going to be great. All right. Cool. So, tea reviews. As mentioned on Twitch. Today, I am drinking the new Ceylon something. I am I'm forbidding myself from buying extra teas. It's so good. It's really good. I'm forbidding myself from buying extra teas because I have way too much tea. And when you have way too much tea and you drink kind of a reasonably unhealthy amount of tea. Oh, they have a new Bamboo Mountain. New release. Full sweet floral fragrance. Oh, it's a green tea. I mean, I'm not against green teas, but I tend to drink black teas. Anyways, if you have, is the Monk's Blend back in stock? No, what? But this says temporarily out of stock here, and this. Okay, anyways, you have too much tea. And you drink an amount of tea that won't destroy your intestines lining, tea will eventually go stale, especially this high quality, et cetera, et cetera. So, yeah. All right. Cool. So, Ethan mentioned on Twitch that one of the applications of reverse engineering is reverse engineering and understanding and keeping old games relevant. I guess there is, let's pull this up, Zelda Ret OOT. Yeah, so people slowly reverse engineering Legend of Zelda. This is great. Of course, this project will die as soon as Nintendo notices it, but a project that didn't die, and that actually successfully took this route is OpenTTD. TTD is Transport Tycoon Deluxe. Let me show it to you. Hold on. We're going to have to... These... Those shelves are way too full. I'm actually scheming a way to reorganize my office to have more shelves. Transport Tycoon Deluxe was a game in the mid-90s for DOS, copyright 1995, Microprose, created by Chris Sawyer, who you might also know and whom we have already mentioned as the creator of Roller Coaster Tycoon. And like Roller Coaster Tycoon, Chris Sawyer wrote Transport Tycoon in x86 assembly, just directly, right? So now that you've done embryo shell coding and looked at reverse engineering, even small programs, you might imagine how difficult this is. But anyways, so he did that, and now decades later. There was actually a project. This is a great closeout to the reverse engineering thing. Actually, I should make this. There was a project called TTD Patch. Maybe 15 years after Transport Tycoon, and TTD Patch was a binary patch to Transport Tycoon Deluxe that would add a lot of new features, fix a lot of bugs, etc., right? TTD Patch was super popular, but it was very hard to work with because everything that you wanted to do to improve Transport Tycoon, you had to do in like, you know, these crazy ways that would then get patched into the original game. And so OpenTTD was born. And OpenTTD, what they did was they disassembled Transport Tycoon Deluxe, and they manually went through the disassembly and they rewrote it in C. It was a manual decompilation effort, and it worked. Transport Tycoon Deluxe is an amazing game. I used to actually, grad school put an end to it, but there were a couple of games I used to go back and replay every single year. Transport Tycoon Deluxe was one of them, with OpenTTD. Another one was One Must Fall. One Must Fall was an early game from Epic Mega Games. Probably also, yeah, copyright 1994, Epic Mega Games. It was an awesome game. I used to go back and replay it every year. And another one was Master of Magic, which I also have. Yeah. Master of Magic. Amazing games. So, anyways, these awesome games, I'd go back and replay it every year, but Transport Tycoon kept growing because of this manual decompilation effort that, of course, it took a while to catch up to the, you know, binary patch method, because the binary patch method started out with they didn't have to decompile something correctly in order to be able to change it. But once it caught up, it just kind of kept zooming on. Now, Transport Tycoon with OpenTTD has like online multiplayer, has a very good modding engine, etc., etc. I highly recommend it. It just came out on Steam, actually. The open source project released itself on Steam, so you can grab it and play it. Super cool. I used to play this every year until graduate school basically eliminated the rest of my free time. And on the discussion on Twitch, there's all sorts of other games that are going through the same thing, right? So we already looked at Zelda Ocarina of Time, reverse engineering process of work in progress, decompilation of Ocarina of Time. Same sort of thing. The same thing happened... Super Mario 64, Ethan says, was fully reverse engineered. That's very cool. Let's see what else happened. Yeah, someone was doing this to Grand Theft Auto, and I think they recently got destroyed because Rockstar / Take-Two is republishing GTA 3 on the Switch, so I guess they remembered that they want to kill anyone working on GTA 3. And then OpenKeeper, also mentioned. Also an open source reimplementation. And I don't know where this went. I mean, I remember when it started. Wow, it's still active. That's awesome. Of the Dungeon Keeper 2 game and engine. Oh, cool. Dungeon Keeper was an amazing game. I didn't replay it every year, but I replayed it often. It's stuck in there. It's hard enough getting games in there, but getting games out of there is a nightmare. But don't worry, I'll get an extra shelf, spread them out, and I'll be able to pull them out easier. Dungeon Keeper 2 is in there as well. And 1. It's an awesome game. I didn't play it every year, but I did play it pretty frequently. And the biggest problem with Dungeon Keeper 2 is the online mode would desync a lot. If you wanted to play with your friends, it was almost impossible. I see. This is an open source remake, not a decompilation. It's written in Java, so we're going to close this tab now. Pretend that didn't happen. And someone else mentioned. Oh, no, I remember. Oh, the other one, Open Lords, I think it was called. Open Lords, Lord of the. Wasn't there an Open Lords? So Lord of the Realms, yeah, Open, maybe. Lord of the Realms was another amazing game. It's also up there somewhere. I'd go back and play it every year. Let's see if it's active. But I think this is also just a re-implementation, not a decompilation. And yeah, it's dead. All right, cool stuff. So one of the use cases of this is of reverse engineering is interoperability, like with OpenTTD, like with if you're a bit younger than OpenTTD, with there was a San Andreas multiplayer mod. There's all sorts of other mods for other games, even when those games don't support modding out of the, like Half-Life and stuff like that, of course, support modding out of the box. But even when a game doesn't support modding out of the box, by reverse engineering and understanding where to make modifications, like you did in Baby Rev levels 9, 10, and 11, for example, you can make a game do whatever you want it to do. It's very fun stuff. Let's see. There's a question on Twitch. Can we reverse engineer IDA Pro? It's actually against IDA's terms of against IDA's end user license agreement to reverse engineer IDA Pro, if I remember correctly. But you could reverse engineer it even without violating the agreement using other tools. All right, awesome stuff. So now we looked at some tea, we looked at some games. Let's look at some slides. What is the state of the class as we enter week 7.5, right? So we're basically halfway through the semester. Baby Rev is now over. Of course, Baby Rev got extended because I was sick. This illness passed much faster than the last illness. Basically today, we're just kind of taking precautions. But next week, I think I'll be back, and hopefully we'll go longer than 2 days between going back to school and daycare and baby Jan infecting me with some new disease. All right. So that'll cover this sort of baby mem delayed memes. There were many of them, and then of course I apparently am a little too wimpy to deal with colds, but it's been a while. Colds are no joke. All right, next category of memes we got were Baby Rev memes. Specifically, this meme was awesome, right? I added this on the bottom of what the meme is about. Of course, in Baby Rev 9, 10, and 11, you have to make small modifications to the binary in order to bypass the otherwise impossible to bypass license key. And the way that this person did it was by changing test EAX, which compared the result of memcomp of your license key against itself, and then checked to make sure that was 0, and if memcomp returns 0, of course you got the correct hash, to XOR EAX, which XORs the result of memcomp against itself. And what does that do? That'll set all of their conditional flags as well. And by setting the conditional flags, it will also set the 0 flag, which because the result is 0, which will allow you to pass the test. That was a great solution, also a great meme, and it is one of these, if you know memes. I like those. All right, a lot of people, of course, when reverse engineering something and not quite getting it correct, had some frustrations with the flag check or the key checker telling them to go away. That's part of the process. And I put this in there, Ethan, just for you. I actually went back after I started streaming and added this to the slides. Reverse engineering Jan 85 is not always easy, especially without symbols. But it's hopefully you have gotten proficient at pattern matching, at least, and recognizing at a slightly higher level of what a certain piece of code does based on previous experience with other code. This is great. The increase in complexity from of the different baby revs. It's pretty good. Especially, the Jan 85. This is all Jan 85 stuff. Full Jan 85. 16, 18, and then 19. It's pretty good stuff. All right. This is a great video summarizing our previous office hours when I went on an insane tangent talking about... let me turn on... One sec. Let me turn on some air here. Perfect. Went off on an insane tangent of GDB scripting. Hopefully it was helpful. But it was kind of... Oh, no. This is different. This is a great meme. This is good stuff. Why is the audio not working? There's the audio. All right. This is what baby rev is like as you slowly gain knowledge of baby rev. Only to see this. And then what happens? We have to wait for it. This happens. That's great. Yeah, it can be frustrating sometimes, especially, after a long while of no sleep, and then nothing is working, and you're just screaming, why won't you just work? And then you start trying random stuff in the hope that something random will work. Then it's time for you to go to sleep, and you just gotta recognize that occurrence, especially in CTF. All right. Let's roll on. What's going on? All right. And basically today we are dropping the baby mem problem set. This is a weak meme from earlier. It's a great meme. Baby mem is no longer, well, it's delayed, but now it's going to drop in about 12 minutes. And in the meantime, I'm going to go through the importance, again, of GDB and so forth. And of course, as you notice, you won't get source code. You need to reverse engineer this with what you learned from the previous module. Of course, the challenges in baby mem aren't as hard in terms of reverse engineering as challenges in the reverse engineering module, but that'll still be fun stuff. All right. Real quick, Scoreboard didn't change in the last 2 days, or at least the top 20, because they had already solved everything. Don't forget, CTF extra credit this weekend, Deconstrue CTF, Tasteless CTF, TSG, and Sacramentum. Tasteless starts tomorrow night. Deconstrue starts tomorrow morning. Tasteless CTF, this is actually incorrect. Tasteless CTF will run for 24 hours. Deconstrue CTF runs for 24 hours. TSG CTF runs for 24 hours. So a lot of CTFs that aren't super long, which is great. The helpfulness, we had an amazing development. Charco is now second place for helpfulness. Zooming upward. Great job. I saw this incredible meme. Also part of the meme review. Last class, we had brainstormed a suggestion because Charco is not an ASU student. They're one of the worldwide students. So what to do with that extra credit that they're earning? Because Charco at this point, I think, has 9.8% of extra credit that isn't going anywhere. Charco has graciously agreed to distribute their helpfulness extra credit evenly across the rest of the class. So we're going to divide that out and add it to everybody. Hence they have become the Robin Hood of pwn.college. Great job. We're going to, if anyone else wants to donate their helpfulness, we'll take that and donate it as well. Awesome. All right. So, Raman's going to steal all of PyPy's flags and give them to the rest of the class. It's a good strategy. All right. As a reminder, for those that missed last class, I've started figuring out how to actually convert this score into extra credit, and it's basically log base 2 and then scaled to the top person. So if you have one helpfulness point, it's very little. 2 or 3, you get big increase, and then it slowly falls off. But especially early on, if you don't have a lot of helpfulness points, you can very quickly get some extra credit percent by helping other people. Awesome. So, where are we in the schedule? We're in the memory corruption module now, very officially in 8 minutes. We will next go on to exploitation next week, and exploitation is going to last through fall break, planned for 2 weeks. It's going to run through a combination of concepts from all the other modules to make sure that you truly understand how everything works together. And at the end of exploitation, if you have all of your challenges done, we will have a yellow belt ceremony and belt some people in class. That'll be fun. And otherwise, you can, of course, finish them all later for your yellow belt. But at that point, you will have an end-to-end understanding of how a security vulnerability in a system can be used to compromise the whole system and achieve the goals of an attacker, right? Which is a very important thing to know. And then from there, we're going to dive onwards into different advanced vulnerabilities, mitigations of, or bypasses of mitigations, and advanced exploitation scenarios. That'll be pretty fun. All right. So exploitation is toddler 1, and then we'll move on from there. I think the rest of this schedule is pretty realistic, with the possible thing of return-oriented programming has historically also been a tough topic. But now, with the death of the side channel module, we will have Veterans Day as Slack in case we need to push it forward. All right, let's see how people did on Baby Rev. Basically, people did all over the place. Baby Rev is definitely, for sure, the hardest module. The interesting thing is that there aren't clusters. Like on Baby Shell, if you look, there are clusters of people that did very poorly, clusters of people that did very well. Baby Rev is much more spread out. Very interesting to see. We actually don't like to see these massive drop-offs, right? These clusters mean that there is some concept that we're not teaching properly. Last year, that massive drop-off happened for Yan 85 in Baby Rev. This year, with the more gradual introduction of Yan 85, I think things worked a little better. We saw fewer people just have completely hit a wall in Yan 85. It still happened, but and we'll continue smoothing that out. But I think we're getting there. There's a question: will the side channel module release after the end of the semester? I would like to make it happen. It's much harder when there isn't like the necessity to launch it. I actually started working on the side channel module in June, and it still is in a very, very very, very incomplete state, but you know, it's one of these deadline-driven things. But if we can make it happen, I'll put it out there. All right. So yeah, Baby Rev saws were all over the place, but still too many people that were in the like E grade for Baby Rev, and as you can see, it's more evenly distributed than the other modules, but we have much fewer A pluses, even fewer A's, fewer B's, or yeah, then a decent amount of B's and so on. This is hard to see, but let's look here. You can very much see that it is definitely the hardest module. It's the only module other than Embryo ASM and Embryo IO where the top 25th where the 25th percentile wasn't at 100% solution, and these ones are like almost 100%. So definitely a tough module. On the other hand, as Pi mentioned on Twitch, this Embryo GDB worked beautifully as a refresher of GDB. Very cool to see people pushing all the way through it. It wasn't meant to be like a blocker. I think we hit the right balance there, hopefully, and maybe there's room for even deeper concepts, but hopefully it prepared people better for using GDB in reversing. The grade distribution graph that makes a little more sense is here. You can see the median was a D in Baby Rev, and that was up until like last night. It was still an E, and I'm like, I don't want to see it being an E, but we got it up to a D, and there's a very wide spread. As you can see, every band has a significant amount of students. I think this is getting through the simple key gens, and then this is getting through the patch me's 9, 10, and 11, and then does that make sense? Yeah, and then this is on past that. Maybe this is the patches, and then this is the pre-Yan 85 where you don't have the Yan code yet, and then this is with Yan code, probably something like that. All right. Or as someone said on on Slack, people just used the Embryo GDB meme to cheese all of Embryo GDB, which is very possible, but it's hopefully that wasn't the case. All right. What do the grades look like? These are the uncurved grades right now. Of course, we already have a small curve. The uncurved grades right now already look fairly good. There are about 16 people, I think, that are that based on access patterns and solve patterns, I think have given up on the class but not yet dropped it. So what we're really, in terms of ease, is somewhere over here, and this is kind of a reasonable distribution with like almost half the class getting A's or A pluses. If we look at the curved grades, taking curves into account, we really have a really nice distribution with just very few people struggling in the class. I'd like to see them, of course, do better, but this is so far good, and the curve is keeping steady, which will be for now. We'll see what Toddler 1 does, but I have confidence that you all can tackle Toddler 1 and beat the crap out of it. It's like taking flags from a toddler. All right, anyways. And with that, we will... there's a question. How many students did we start with? We started with 150 students. 155. Let me see what... I have a analysis per module. So Embryo IO cost us 52 students. So 103 students solved anything in Embryo IO. 95 students solved anything in Baby Suid, so that was an extra 8 students. Then 2 students came back. Embryo SM has 97 students that solved anything. Baby Shell, 97 students that solved anything. Baby Jail, 93. embryo GDB 94, and baby rev 86. So from 155 or so, we're at 86 people that have solved anything in baby rev, which is not a not abnormal for prior years. Cool. Okay, so Baby Mem. We're launching Baby Mem. It'll teach you about the impact of memory errors on software security. The challenge problems, due in 1 week, 4 p.m. as always. The biggest thing that I can tell you about exploitation is looking at things in IDA is not going to cut it. You can understand a vulnerability, the presence of a vulnerability, by looking at things statically. But you can't understand the behavior of it as you're trying to exploit it without some dynamic analysis. 99% of the questions Connor and I get from here onwards in the class is, why doesn't my exploit work? And 90% of the answers is, did you look and single step it in GDB? If you haven't single stepped something in GDB, then you are not giving yourself the tools that you need to understand your exploit and what's going wrong. So please, Embryo GDB was there for a reason. Please don't forget about your good friend GDB. It's going to, without GDB, quite frankly, it's impossible to pass the rest of this course. You need to use GDB. No breaking up with GDB. Mega baby roar. All right. Let's see. Catching up on Twitch. All right. There's a question. Is it bad that I never moved on from vanilla GDB? No, it's totally fine. Vanilla GDB, I mostly use vanilla GDB, in part because there's nothing worse than running into some corner case in pwn debug that during a lecture and spending time diving into why it doesn't work. Vanilla GDB is fine as long as you use it properly. Of course, for really complex, crazy stuff, the various helper functionality in pwn debug and Jeff helps, and maybe for what's it called, for a baby heap, you can start exploring that if you want to, but realistically, you don't need the other crazy stuff. Excuse me. You need a debugger that you know how to use, whether that's vanilla GDB or GDB with add-ons. All right. Cool. So, Connor, is it live? Let's go look at the dojo. They are live. So 30 levels of Baby Mem. Each level has, again, a teaching and a testing mode. The teaching mode will go a long way trying to help you. It'll tell you all of the addresses involved. It'll show you the layout of the stack before and after you clobber it. All sorts of stuff. Of course, I really hope you have watched all of these lectures. You will need to understand memory disclosures in the later levels. You'll need to understand ASLR, stack canaries as you move through this. But the basics are pretty simple. And I will now walk through not these levels, but the concept of using GDB and using other tools to understand a challenge dynamically rather than statically. And that'll be kind of the live demo for today. All right, so now that I'm all hydrated, let's make this happen. I'm going to do this here. I'm going to create a vulnerable program. All right, and our vulnerable program is going to be pretty simple. We're going to have a buffer that's 16 bytes long, and we're going to let's have a win function. You'll see it for the win function in most of the challenges in this module. Thank you for catching my typo on Twitch there. All right. The win function will just tell me I won. Let's just do puts here. Puts win, and then we will we'll open the flag and read out of that into the flag buff, whatever, 1024 characters, and we'll write all of that to std out. Okay, perfect. Then we'll do the simplest possible overflow and read from standard in into the buffer 128 bytes. All right, nice and simple. I'm going to also compile it nice and simple. No stack protector and no, wait, no, it has to be here, and no position dependent code. Include some more stuff. Include some more stuff. It's not a pointer here. It's 0 or O read only. All right. Okay. No problem. It all works. If I do a bunch of A's, segfault. Okay. So let's start out looking at this in IDA like a dummy. No, I'm just kidding. Start out looking at things statically if you want, but we're going to move very quickly to a dynamic situation. All right, and now we will, hold on, let me get the correct thing shared. Okay, resize it. You know, I am very close to like spinning up an embedded X server in a window to output stuff too, so I can share that whole desktop. I think that will probably be less disruptive than resizing IDA all the time. All right. So here's my terminal. We're running the thing. Here's IDA. Here is main, very short main. We tab. If you want to decompile, we see, okay, here's this read from the buffer into read into the buffer of hex 80, and the buffer is size 16, and all hell is gonna break loose, right? Now the question is, what's our goal? That's really the question. The question of what's our goal is in this case, our goal generally is to hijack control flow to get the flag. Or really, our goal is to get the flag, however that's done. In order to do that, we can see that we can overflow the buffer in this function, override the return address. What do we do with that? We can redirect program execution. What do we do with that? In order to achieve our goal of getting the flag, well, we see that there's a win function that will get the flag for us. Let's play around with that win function. Hey, in GDB, to make sure it does what we think it does, can GDB vuln, we can start it to break in main, or start I to break in start, and we could call win just to make sure. And that is, in fact, what Win does. Now, of course, you can only do this in practice mode, really, on the real infrastructure, because once you launch something in GDB, that's set UID, it'll drop that. It won't be launched as root. Sorry, choked on my tea. That tea can pack a bit of a kick. I'm gonna put you guys on mute for a second to cough my lungs out. I'll be right back. I'm back. All right. Whew. So we called Win. That's great. Go us. We've confirmed dynamically that Win does what we think it does, which always good to be sure. But normally Win is a-okay. All right. Cool. If you see a function named Win in this class, it's going to most likely give you the flag, but double check. So that was great. We now know what we have to do. We have to use this overflow in main to overwrite the return address so that when main returns, we return to Win. Now, how do we do that? Well, we need to write the appropriate amount of data. And as part of that data, we need to write the address of Win. In this case, this is not a position-independent executable because I compiled it to be not a position-independent executable, but later in the challenges, you will have to deal with position-independent executables. But for now, we can just take this whole thing and overwrite take the address, overwrite the return address with the saved, take the address of Win, find the location of the saved return address of main, the offset from our buffer, and overwrite it. How do we do that, though? One way is to look at the decompilation and say, okay, we start writing to buff. Buff is located at the saved base pointer minus 10 hex. The saved base pointer will point to the rightmost side of the stack frame, and then we'll be 16 bytes to the left of that. So we can, you might say, okay, in order to override that, and keep in mind, we're doing this statically, exactly like I told you is not the optimal way, in my opinion. But you could say, okay, statically it makes sense, 16 bytes, and then we have to overwrite with our return address, right? You'd be wrong. And let's just go down the rabbit hole pretending that we are doing it that way. So what do we do? Very easy. Let me go into the right version. Pwn tools has a pwn command that'll let you write in hex, and it'll unhex it. Anyways, so this is 16 bytes. Yeah, 16 A's, right? And then, let's say first, we're not going to shoot for the stars right away. We're going to try to redirect. Usually, your first attempt at the exploitation will just redirect control flow somewhere where you can tell that you got it right. So let's do 4-1, and then 4-2, 4-2, 4-2, 4-2, 4-2, 4-2, 4-2, 4-2, 8 B's. 24 total. And then we pipe that into our vulnerable function, and it doesn't crash. You say, what the hell? And of course, what the hell is that we're overwriting the saved return the saved base pointer that RBP points at instead of the return address. If we look at the assembly, which is now where you have to start looking to understand the true impact, here is the creation of this, the allocation on the stack of this buffer, 16 bytes left, right? So RSP points to the beginning of our buffer. RBP is where RSP was, points to the same location that RSP points to. It was equal to RSP. In fact, RSP was moved into it before the subtraction happened. Again, they bound the right and the left side of the buffer, of the stack frame. RBP when frame pointers are being used, and then RSP is on the left side, right? And our buffer and other local variables in a program, in a function, which in this function there are none, is just our buffer, are in between. So what is there? We have so what does RBP itself point to? RBP points to this last pushed thing, which is the old base pointer that was valid in libc start main before libc start main called main. And then after that is our return address from our program. Let me actually demonstrate this to you using another example. We're going to create callstack.c, and we're going to have int main that calls int a, that calls, or void a, let's say. This can be void main, this will be a, and this will call C. Okay, so main will call A, which will call B, which will call C, which will write out something inspiring. Okay. And let's compile it with the same way without a canary. You'll see that later on. And without position-dependent code. All right. We run it. It outputs yeah. We look at it in GDB. Okay. Let's start it up. Oops, not start I. Let's start it and break at main. We can look at our backtrace in the program, and GDB only traces all the way back to main, but we can see if we look at the 8 giant 8-byte words in RSP, we can see there's already stuff on the stack, and this is going to be depending on where we are in main. Yeah, we're at the very beginning. So this main just got called. This is going to be the address where main was called in libc start main. If we back up 5 bytes, this is the address where it'll return to. And if we, oh, okay, call RAX is a 2-byte instruction. Yeah. So if we back up 2 bytes, we see that call RAX. And of course, if we look at what RAX currently points to, it points to main. And that was passed in to libc start main from start. All right. Anyways, we're in main. The stack, it has the return address in that will return into main. And if we disassemble the next 5 instructions, we'll see that we're about to set up main stack frame. Let's see what we're going to push the old frame pointer in libc start main, which is 0. Why? Libc start main, or libc in general, is compiled with optimizations that don't use the frame pointer. Those exist. They're very easy to enable. In fact, if you enable advanced optimizations in GCC, it'll automatically start doing that. It makes things harder to debug because it's much harder to see to walk up the stack perfectly, stack frame to stack frame. These base pointers give you a very nice single linked list of stack frames, basically. But these base pointers aren't needed. You can reference local variables using our SP plus something as easily as you can do our BP minus something, right? So libc isn't compiled with base pointers enabled, but that's fine. Our main doesn't know about that. It saves it anyways. What it costs it 8 bytes on the stack. All right. So we step past that push, and then of course it moves the sets the this frame's base pointer by writing the stack pointer into it. So now our frame is of 0 size. The stack pointer and the base pointer point to the same location, and then it calls the next function. So let's look at what's going on our stack. We have the saved base pointer from libc. We have the saved return address from libc. And if we step into this call, of course, puts the saved return, the address of the next instruction after the call, which is where the callee will return to. So we are now, if you look at where we're in A, and GDB, of course, crawls the stack to get this information and says, hey, this is where you're going to return to in main. That's exactly what's on our stack. And that is a no-op that is 5 bytes after our call instruction, the next instruction after call. Cool. Here we see the same thing in A. We save the base pointer, which now is actually set because this program is compiled without the optimization that takes out base pointers. We'll save the base pointer of main because we don't want to mess with that. Shit, no, we didn't do that yet. There we go. Now we save the base pointer. So now our stack is base pointer of main, return address into main, base pointer of libc start main, return address into libc start main. And then we will set up our base pointer, which is currently pointing to the stack pointer because we have no local variables in this function. And we're going to call B. And again, when we call B, oops, here we go. When we call B, our stack is the return address when B starts executing. The first thing on the stack is the return address into A right after B was called. And when we ret, you'll see that this is exactly where it goes. Then the saved base pointer that B saved from A. No, sorry. This is the return address into A. The saved base pointer that A saved from main, the return address that A will follow back into main, the saved base pointer that main saved from libc, and the return address that main will follow back into libc start main. All right, and of course, what will B do? B will push the save the base pointer from A, set up its own stack frame, and now on the stack is the saved base pointer from A, the saved return address that we'll take into A, the saved base pointer from main, the saved return address that A will take into main, the saved base pointer from libc start main, and the return address that main will take into libc start main when it returns. And then we'll call C. Okay, and what will C do? Same thing. It'll push. C starts out with the return address into B on the stack, and we just pushed the frame pointer of B to save that. And now, again, the saved base pointer from B, return address into B, saved base pointer from A, return address into A, saved base pointer from main, return address into main, saved base pointer from libc, which doesn't use base pointers, return address into libc. Awesome. All right. And then C will call puts. So let's walk into puts. Okay. And what does this look like now? return address into C from puts. This is where puts will go when it returns. The saved base pointer that C saved from B, the return address from C into B, and so on, right? And if you notice, if we start walking here, puts, this is the resolution, the resolver stub of puts to resolve the actual puts library function. Where are we? We're in libc. We're in fucking piece of shit. We're in the resolver code now. This is not where we wanted to go. Okay, now we're in puts. Awesome. Phew. Puts saves a bunch of stuff because it uses a lot of registers, including the base pointer. Even though puts doesn't use the base pointer itself, it saves it off because it will use it for general as a general purpose register, likely. And puts doesn't use it because libc is compiled without using base pointers. And if you look now at the stack, there's just a bunch of insanity that puts saved onto the stack because it's actually using it. All sorts of stuff. And then here is the return address from puts into C to C plus 20. Of course, that's 5 bytes after our call to the puts resolver stub. The saved base pointer from that C saved from B, the return address into B, and so on, right? If we finish puts, that was something that puts called. If we finish puts, here we go. We return into B. And of course puts popped stuff back off the stack. So if we look at our stack again, saved frame pointer from B, saved the return address into B, and so on and so on. Let's step through. What does C do? C restores off the stack, pops off the saved base pointer from B. So it restores RBP to what's it called? My mind just went blank. It restores RBP back to the saved to B's RBP, and of course afterwards, I did you a disservice by not having any local variables, because afterwards it also restores. Before this, if we had local variables, the reason the snop is here is if we had local variables instead of the snop, you would shift the stack back to the base pointer to deallocate the stack frame. Then we pop off the saved return address. So here it is before. We pop off the saved frame pointer. If we step here, we're about to return. We popped off the stack, the saved frame pointer. RBP is now B's RBP, the old value that B launched C, that was an RBP when B launched C. And we're about to do a ret, which will take the value at the top of the stack and jump there. So it pops off. A ret is equivalent to pop RIP. We step. We're back in exactly this address, 40115F. Here it is. And now we look at our stack and the saved base pointer from A beckons. We're about to pop it off. And now we return back into A. And now if we look at our stack, the saved base pointer from main beckons, and then the return address into main. We pop off the saved base pointer. Now we're about to go to this 401.189. Boom, there we are. And what do we do now? We restore the saved base pointer from libc. If you don't know, libc might have been using it for something important. I mean, it's 0, but that could be an important 0. So let's, by the normal calling convention used in well, at least in Linux and AMD 64, but also in most other, for AMD 64 and most other platforms, RBP is what's known as a callee save register. That means if you want to use it, make sure to give it back in the same state you found it. All right, so you save it off, you use it, then you restore it. All right, so we saved it off. So we are going to restore it, and then we are going to return back to this address, which is now at the top of the stack, which is in libc start main, and that's after that it'll finish up the rest of the program. Cool. All right. I know that was a little bit of a dive, especially on a tangent, but let's go back to Vuln, which this explains why Vuln, when we gave it 24 characters, didn't crash. We overrode, of course, our buffer, which was the 16-byte this 16-byte area that was allocated onto the stack frame. It's not always the whole stack frame that your buffer takes up, but in this case it is. And then we overwrote the saved RBP. And that was processed by this leave function. Leave is a meta, or it's a what's it called? It's basic. It's a composite instruction that does deallocates the stack frame, moves RBP into RSP, right? Boom, and then pops RBP, pops that saved base pointer. All right, so and then we return. So we managed to overwrite the saved base pointer, which evidently isn't critically important to libc, or at least doesn't make it crash, which means we were right up against the return address. So let's just do another one. 43434343434343. Boom. Segmentation fault. Okay. How do we know that we crashed at the place we want to crash, and as in at 43434343, and not that this overrode something else critical that made the program crash? Well, GDB. Actually, two ways. One is we can look at our kernel message log, but I don't know if you can do this on the infrastructure. Changes year to year. And we can see where we crashed. No, we can't. That's right, because we crashed trying to jump to unmapped memory. All right. The right way is GDB. So let's save this into our attack. And then let's do GDB vuln, run it with that attack, and boom, it gets a crash at this location. What is this? This is ret. And where are we returning? Of course, ret is the same as pop RDI. We're returning to 434343. Big success. Awesome. Okay, but this is a bit of a problem that I'll touch on next, because we are running this program now in GDB, and GDB makes some slight changes to memory layout and so forth that can really wreck your exploit. All right, so we'll dive into ways to avoid this, but let's first show you another way. When you run something that crashes, it's segfaults. And Linux has this built-in capability to save an image, not like a picture, but like to save basically a process as it crashes. That's called a core dump. If you look at various process limits, one of them is the core file size. Core file size says how big the maximum size of a core dump is, and by default it's 0. If you put it to unlimited and then crash this, now it says segmentation fault core dumped. A much nicer message. And we have this core file, which is actually an ELF. You can't execute it without some work, but it's an ELF that you can open in GDB that contains your entire memory space of your process as it crashed. It's not small. Well, it is small. I guess this is a tiny process, but it is bigger than my vuln program, because it also contains, I guess it probably doesn't contain libc by default. Does it? Anyways, it contains enough information for you to figure out what the hell happened right at the end of this process's execution. the way you load a core dump is you say, I'm going to gdb vuln, and please load this core dump. And this actually drops you into GDB right at the end with memory and registers loaded from the core dump. And just like if I had run this in GDB, I can info-reg. I can see, oh look, we did overwrite RBP, the saved return base pointer, the saved base pointer from main with all B's, and then it got popped. And now I can do that same thing, RSP, and see that we overwrote this, the saved return with 434343. Amazing. So we're basically there. We just need to redirect that to the win function, and we win. Where's the win function? Well, there's no SLR, so the win function is right here, 401,196. Let's do that in little endian ourselves, because we're over here anyways. So, in little endian, oops, it is 961140, and then the rest zeros. That was 3. 1, 2, 3, 4, 5. All right, hit it. Boom. Redirected execution right into the win function. Let me show you how this works, single stepping it in GDB. Actually, we'll start it with X. Okay, so here we go. We've set up our stack frame. Let's look at what's on the stack right now. What's on the stack is some shit that was here before. When we allocated this, oh, we haven't allocated yet. Boom. Okay, we've allocated the stack frame. What's on here? Some stuff that was here before, whatever this was. The stack doesn't get cleared, as you will explore much later in this module. The stack doesn't, like when you do sub RSP 10, it just, you know, gives you 10 bytes of room in the frame by shifting the stack pointer to the left. It doesn't clear what was there before, unless that was explicitly cleared. That's the source of an enormous amount of crypto vulnerabilities, actually, because you start leaking important things like keys, or later on in this module, as you'll find out, addresses. All right, and then there's the saved return, the saved base pointer from main, and the return address, the saved base pointer from libc start main, and the return address into libc start main. We're going to step all the way up until this call to read. We'll step over it using next instruction. Boom. Now let's look at what happened to the stack. Our buffer of A's, and then the overflow into the saved return, saved base pointer, sorry, from libc start main, and the saved return address, where main will return to, which is no longer into libc start main. It used to be into libc start main, but is now going to win. And if we step, what happens here? We set the return value of main. Main will return 0. We do this leave, which will clean up the stack frame, not overwrite anything with 0 or anything, but just shift RSP all the way to the left, all the way to the right to RBP, and it'll pop RBP. Boom. Let's look at where our stack is now. Top of our stack is the return address, because we're about to return there. And in RBP is the value that we had written into the saved return, the saved base pointer, excuse me. And if we continue, boom, we won. And then, of course, we crash because the rest of the stack doesn't make sense. Because win will try to return, of course, and we didn't write a good address for it to return to, and it'll probably return seemingly somewhere random. Cool. All right. So, core dumps are very useful. What did that teach us already? Well, hey, we started out looking at things statically, and you'll see that I kind of ninja'd you into a dynamic view anyways in GDB with core dumps and stuff. We could have avoided it. We could, of course, because mostly did that to verify in this case. We could have reasoned, okay, yeah, we know that there's the base pointers, right? You know, you can see the code right here. So there is this 16 plus the 8 bytes that leave pops off, and then the return address. And we know what the return address is, and so we put it over here. We put this, we know what the return address that we want is, so we, you know, put it in here and so forth, and we do this completely statically, no looking at GDB, etc., etc. Well, you can do that. It gets more and more complex, but good luck. But we can also do the opposite. We can say, hey, I don't know what the hell is going on with this program. I just know there's a buffer overflow. Let's just fucking solve it, right? pwn.college has something, pwn.tools has something called a cyclic pattern. Not cycling, cyclic. You can say, give me a 128 byte cyclic pattern. And a cyclic pattern is something where you can give it you use this cyclic pattern to trigger whatever, some functionality in a program, and then you see a specific part of memory or something, and you see, okay, this part of the cyclic pattern was in this part of memory, and the way that a cyclic pattern works is given a part of it, it can tell you the offset. It's a bunch of unique cycling, and so you can say, give me this offset. God damn it, it needs by default exactly 4 bytes. -L. And it says this is offset 40. Boom. Can we do longer? No, it needs to be exactly 4 bytes. But of course, we're on a 64-bit system, so in order to just be able to copy paste stuff easily, you can set this -N. So give me a 8-byte cyclic pattern. Oh, not that big. By default, it gives you a very large cyclic pattern, so let's give it 120. So this is an 8-byte stride cyclic pattern. You can see here's 8 bytes, here's the next 8 bytes, here's the next 8 bytes, and any of these 8 bytes, it can uniquely identify. If I ask for a 1000 cyclic pattern, I mean, you get the idea, right? Each one of these is more or less unique, but even this partway through is unique. So I can say, I got this. Where was it? It was, that was 9 bytes. That was at location 244. Even offsets and so forth work. How do we use it? Easy. You take a 128 byte cyclic pattern in this case, because I know the read is 128 bytes. How do I know that? Let's just strace vuln. I see that it had tried to read 128 bytes. Okay, that's fine. I give it a 128 byte cyclic pattern. It seg faults and dumps a core. I load that core in GDB. I see what's in RSP. Here's what was in RSP. And I say, look up this. It says that's at offset 24. And look, I even put it in as a number and it did the right thing. I didn't know if that would work. Keep in mind endianness and so forth when you do this. But I guess pwn.tools handles that automatically if you give it as a number. That's pretty neat. Okay, so it says offset 24. So I know at offset 24 is the beginning of my address, and then I can do this exact same thing. Let's just, to show you, here is this. That's the return address that I want. And then here I will do something crazy. Is there a pwn.tools? There's got to be a pwn.tools. Oh, I can just give it. I can give it a pwn cyclic 24. Give it 24 bytes, and then this return address. Oh no, that didn't work because pwn cyclic 24. I need pwn cyclic 48 because this will be on. No, okay. Let's be clever. I'm gonna generate cyclic 24 bytes of padding, and then our address. I'll send this to X, and then boom. Success. And that was doable on this very, very simple example without even opening IDA, right? We figured out, we created a cyclic pattern. We sent it into vuln, the program. That crashed and dumped a core. We loaded the core dump in GDB. We looked at what the saved return address was. We looked up where, or had gotten overwritten with, rather. We looked up where that data was in the cyclic pattern. So it started off at offset 24. We created some padding of 24 bytes. And then our address created an input file. And then we send that input file into vuln. And it worked. Now, this is a very simple example, and really you should be using pwn tools in Python to interact with this stuff, because past the first couple of levels, you will need to interact and leak and all of this stuff. But here's an example of a completely dynamic approach to this. Now, neither a completely dynamic approach nor a completely static approach are the right way to go. You're going to need a joint approach. Use all the tools at your disposal. But if you're trying to exploit something and it's not working, look at it in GDB. Awesome. All right. One thing that I want to mention, I know we're now officially over time, but I wanted to mention one important thing. If I model print, what should I call this? Yo.c, whatever. Let's say I have a function yo, and it has a buffer called yo, 128 buffer. And I'm sure this will backfire. If I print out the address of yo, and let's just, same sort of thing, that's not relevant, but this is. Here is yo, printing out the address of the yo stack buffer. And you, son of a, that's a lot of randomness. Did I fuck this up? I need something more stable. Let's do... Hold on, let me align this carefully. Okay. This is going to have to wait for, I think, my next office hours. I'll figure out. Basically, there are subtleties that can occur between running something in GDB and running something outside of GDB. Let me give you an example that actually will for sure work. You remember running things without environment variables using env-i. So let's do env-i. Okay, now I'm in a shell without any Jesus Christ. Okay. No. Fuck. All right. Hold on. Rather than trying to fix that, we're gonna abort into another terminal. All right. Sorry, I pressed the wrong button, and now we all have to suffer. Okay, so we're back. Let me get, yep. This is from last time, my screen session. Okay, awesome. Okay. So we are, let me get my mind back together. Okay, let me show you a difference between launching something in GDB and launching something not in GDB. And instead of, yeah, here's what we're going to do. Yo is going to print out all of our environment variables. All right, this is going to print out all of our environment variables. Nope. That's fine. No. Puts. We have to dereference that. All right. Print out all of our environment variables. Boom. All right, and then it's sec false. Why? Why would it sec fault? That shouldn't sec fault. Okay, it doesn't matter. Here's all of our environment variables when run. I have a lot of environment variables set up, right? If I run it with no environment variables, okay, no environment variables here. Let's say I run it with an environment variable, whatever, ASDF equals FDSA. Okay, here's my one environment variable. Okay, hold on. Let's make it not sec fault. That's really bugging me. So, oh, this is why. There we go. Success. Okay. All right, so here is us running it with, let me run a shell with no environment variables. All right, very few environment variables at least. Here's yo. Just have my ASDF environment variable and the working directory. If I GDB yo and I run it, GDB adds a couple of environment variables, 2 specific ones for some fucking reason. Adds the variable lines and the variable columns. It's a very small change, but those variables take space on the stack and they push the stack a little bit. And they actually misalign the alignment of the stack will change in GDB and outside of GDB. So be very careful if you have an exploit that depends byte to byte on overriding perfectly stuff on the stack. It could, in certain cases, get screwed up when running in GDB versus outside of GDB. How do you work around that? Well, a core dump is always going to be fine. Right, core dump runs outside of GDB, and then you can post-mortem try to figure out what's going on. Pwn tools, when it invokes the debugger through GDB, I think it does better. The other way is you can use GDB server. So I run yo and GDB server. GDB server. Oh my god, this shell is unusable. GDB server is will start GDB and will listen for and you can attach from GDB into from a GDB client to your GDB server. So you can do GDB server yo. Oops. GDB server yo. What am I doing wrong? Oh, com. I need to tell it. Yeah, I need to tell it to listen on GDB server localhost. You need to give it a port. Yo. All right. So GDB server started up yo and is waiting for me to connect from GDB on port 4000. And here I can do GDB yo and I can do target localhost 4000. Remote localhost 4000. As you can tell, help target remote target remote localhost 4000. Boom. And I connected to this yo running GDB server using the GDB client. And if I continue here, I can see the environment is fine, right? The other thing that you should watch out for is you can run yo here. Let's change yo to also do the same with the arguments. Okay, so, no, what? Do the same thing with the arguments. Okay, arguments is /yo. Depending on how you run things, depending on how you run GDB, if you run yo here, GDB will use the full path. That also is stored on the stack, all of the arguments. And so that can also shift the stack. So be very careful about these effects. I think that's the only effects, environment variables and the arguments that happen in GDB. And this will also happen in GDB server, unfortunately. Okay, GDB server port 4000, and GDB yo, target remote 4000, continue. No, it doesn't happen in GDB server. Why doesn't that happen in GDB server? Why doesn't GDB server set additional environment variables? Interestingly enough, you would expect GDB client and GDB server to use the same code base. They don't. GDB server is a separate code base from GDB due to historical crazy reasons. But I actually prefer, whenever I can, to use GDB server with a GDB attached to it. As you saw, this actually took a little bit of time, right? Because this involves transfer over sockets and so forth. So like several bytes at a time. So it's suboptimal in many ways, though. It's much slower, but you don't really care about that in this case. GDB server is your friend. Cool. All right. So in this lecture, we have covered the need to verify stuff dynamically. We have covered the use of core dumps, covered the use of cyclic patterns, covered the use of GDB server to keep things as close to actual execution as possible. Any questions on any of that? All right. I either got disconnected on my iPad or there are no questions. I will then let you go. Sorry for taking up an extra 15 minutes, but I guess we should all be used to it by now. I used to do this class in 1 3-hour-long lecture per week, which made things more complicated in terms of extensions and stuff, because we couldn't do a half-week extension. But anyways, it's a different issue. And I would still go over, even on the 3 hours. So, yeah, sorry about that. Anyways, good luck. Let's take a quick look and see where people are. Wow, people are on level 6.1 already. Amazing. Of course, there are 15 levels. Scoreboard is looking... D-Rock Delta is on the top of the scoreboard with PyPy and Frosty Feet and S. Radley and Trees closing out the top 5. Good luck, everybody. And I will see you next week. Remember, 1 week, don't put this off until the last minute. Please, I'm begging you. A lot of people did that for Baby Rev and hit a wall. This is trickier in many ways. Please do this ASAP. In fact, for next year, I'm going to introduce an extra credit category just based on how early people tackle the homework or something. I don't know. Maybe we won't do it this year, most likely, but you know, something to keep the last minuteness out. I know that's how I function too, but it's not the optimal way of functioning. All right. Anyways, good luck on Baby Mem, and see you next week.